Okay, so one of the things that we can observe anytime we form a carbocation is a so-called carbocation rearrangement. Anytime you form a secondary carbocation, there is the possibility that it may rearrange. Now, the possibility means it could, doesn't mean that it will. And so the only time you're going to see a carbocation rearrangement is when I can take a secondary carbocation and turn it into a tertiary carbocation. Okay, so we're going to go through the mechanism of this dehydration here, this alcohol, and we're going to use tosyl sulfonic acid. And has this, well, it doesn't have the structure, but I'm going to abbreviate it. First step, of course, is to turn my OH into a good leaving group. I'm going to form water. As soon as I do that, this thing is free to leave because water is a great living group. And this is going to be formation of the carbocation. Okay, so a couple of things can happen from here. Okay, so I'm going to take a look at the type of carbocation I formed, and sure enough, that is a secondary carbocation. So of all the carbocations that we form, this is the least stable. As a matter of fact, they're pretty hard to form. Okay, and so we can proceed via the reaction normally. In other words, we can do beta hydrogen elimination and form our two alkenes, okay, from this particular intermediate species, or we can see a carbocation rearrangement. So I'm just going to go through the normal mechanism first, okay, what one would expect. And I'm going to go ahead and I'm going to identify the two types of different hydrogens I have. So by looking closely, I have this beta hydrogen here that I can eliminate. And then I also have this beta hydrogen here that I can eliminate. Okay, so we're going to go through the reaction that's going to happen before any carbocation rearrangement. Now, remember, all of this is happening all at once. Remember, you don't just have one molecule or one carbocation. We probably have, like 10 to the 20. So remember, we're doing a reaction. All right, so let's go ahead and let's look at the elimination of the green beta hydrogen first. So the tosylate that I formed in the previous step is going to come in. It's going to remove that proton, and I'm going to form that bond. Oops, looks like I added an extra carbon. Okay, so this methyl over here is going to remain unaffected. And then what I'm going to have over here is I'm going to have this new alkene here. Okay. Now again, tosylate can come and remove this proton. And I'm going to see the formation of this carbocation. I'm sorry, of this alkene. Now, once I form that bond between those two carbons, that one methyl that was a dash is now a straight line because now the carbon that's attached to is sp2. Okay, so that's normal. That's the way we used to look at them before any carbocation rearrangements. But now we're going to look at a carbocation rearrangement, or look at a possibility that may happen. Okay, so when I have a secondary carbocation next to a tertiary hydrogen, and I mean next to. In other words, I mean that the two carbons are adjacent. They must be directly next to. What I can see is a 1, 2 hydride shift. Now, when I say hydride, that's what I'm talking about, right? I'm talking about the hydrogen anion. Again, the whole reason this happens is what? Okay, it's to go to a lower state of energy. And so what I can see here is the hydrogen that's next to the carbocation will move, taking the electrons with it. And so this rearrangement will produce this carbocation having just moved this beta hydrogen over here. Okay, and so now this carbocation can undergo the series of elimination reactions. And so what we're going to see is when you have a secondary carbocation that can rearrange, you're going to see the formation of products that may have happened before or after. Now, I'm going to go ahead and I'm going to eliminate. Now, I looked at those two terminal methyl groups coming off that isopropyl. Now, they are equivalent, so they're going to result in the same alkene. So I'm not going to do two separate mechanisms for them. But again, they come in here, remember, ever lurking in the background, waiting ever so patiently is my tosylate. So tosylate will come and remove first this beta hydrogen first. And so what you notice is you can actually form the same compound both before and after the rearrangement. And there's absolutely no way to tell how it was formed, right? And so, and this is not uncommon. A lot of times when you have hydride shifts, you're going to be able to form the same compound through two different mechanisms, two different pathways, because this one was formed before and this one was formed after. Now we're going to go ahead and we're going to eliminate one of those purple hydrides. So let's come down here. I'm just going to go ahead and eliminate the one on the top because that's how I feel, but you could very easily have eliminated the one on the bottom. Okay, and so the tosylate will come, remove that hydrogen, proton rather, and then I'm going to form this alkene here. Okay, which can only be formed after. So when you look at the total number of products you can form, okay, you have this compound here, the top, which can only be formed before carbocation rearrangement. You have this one, which can be formed before and after carbocation rearrangement. And then you have the last one that we formed that can only be formed after carbocation rearrangement. And so for this particular reaction, you would expect three different products.